Hello, today we will solve some of the important problems from diffraction, and I strongly believe that if you can able to solve this problem, you can solve any problem from diffraction. Here is the first question on diffraction. The question is, find the position of first minimum for the single slit of width this much and a screen at a distance of 2 meter from the slit, and the wavelength of the incident light is 632.8 nanometer when it's shown on the slit. Okay, we have to find the position of first minimum from the central maximum, the distance between the first minimum and the central maximum. This is y. We have to find the value of y. Okay, so before doing that, we'll try to find the value of theta in terms of the known parameter. From the trigonometry, I can write tan of this theta as y by d, and from the small angle approximation we know sine of small theta is equal to the theta itself. Similarly, the cosine of this small value will be 1. In the when theta tends to 0, cos 0 will become 1. So therefore, when in the limit theta tends to 0, tan theta can be approximated as theta. So from equation 2 and 4, sin theta is approximately equal to tan theta, and that is again approximately equal to theta itself. So what is given in the problem? Slit width is given, distance between the slit and screen is given, and lambda is given, and order of minimum is equal to 1. We know the diffraction minimum is governed by this equation, and putting here n is equal to 1 gives me this equation. Rearranging this we get lambda sin theta is equal to lambda by d. And from equation 1 again tan theta we know y by d, and tan theta is approximately equal to sin theta. Therefore, sin theta is again equal to y by d. Therefore, putting this sin theta in equation 5 gives me, so rearranging this we get y as d sin theta, and put this sin theta here. We get y is equal to d times lambda by d, and y is equal to this, and putting all the known parameter gives me the y value as 3.16 centimeter. So this means that from the central maxima, my first maxima is located at 3.16 centimeter distance. That's all. Here is the second problem on diffraction. Here the question is, we have a single slit of 0.2 centimeter wide and a 1 meter distant screen. Suppose in the experiment, if the second maximum occurs at a position of 1 centimeter along the screen, what must be the wavelength of light? So here the position of second maximum is given, that is 1 centimeter from the central maximum, and they are asking to find the wavelength of incident light. So A is given, slit width is given, and D is given. To find the lambda, wavelength of incident light. These are the given information. As I told, slit width 0.2 centimeter, D is equal to 1 centimeter, and Y2 second maximum position is 1 centimeter from the central maxima, and order of maximum is 2. And the solution is, so from the small angle approximation we know tan theta is approximately equal to sin theta, and then again that is approximately equal to theta. So tan of this theta is equal to y2 by capital D, and that is given by tan theta is equal to y2 by d and 0.01 radians. So this is approximately equal to theta 2, and that is 0.01 radians. So from we know the maximas in diffractions are given by this equation, 2m plus 1 lambda by 2. Rearranging this equation for lambda we get this, and putting all the values, known values, we get lambda. So this is just a simplification, simple calculation you have to do, and it turns out that lambda as 8000 nanometer, which is much larger. So as per the given values, the lambda is coming as this much. Here is another problem from diffraction. If 700 nanometer light falls on the slit of 25 micrometer wide, what is the full angular width of central diffraction peak? So if theta is the position at which the first minimum occurs, then this is the extent of angular width of central maximum on either side. So 2 theta will be the full angular width of central maximum. And we know in diffraction the minimas are governed by this equation, and substituting here for n is equal to 1, we get this equation, and rearranging this we get theta 1 as sine inverse of lambda by a. And in this equation, substituting the known values, 1 will get this equation, theta 1 is equal to sine inverse of this, and simplifying this we give this, and theta 1 is equal to sine inverse of 0.028, and this is approximately equal to 0.028. So this theta 1 is the half angular width. For full angular width, one has to multiply by 2. This is the full angular width of central maximum for the given parameters. Here is another similar problem from a diffraction. How wide is the central diffraction peak on a screen at 3 meter behind a slit whose width is 0.045 millimeter and light of is illuminated by a light of wavelength of 600 nanometer light. Here what is asked with linear width of central maximum is asked. So what is given is capital D A lambda is given, and we know the linear extent of means extent of first minimum on either side of the central maximum is given by this formula. So if you multiply this by 2, this would be the width of central maximum. Okay, now putting all the values here, one will get 2x as this much. So this is your central maximum, width of central maximum, that is 8 centimeter or 0.08 meter. Thanks for watching and subscribe.